So, all of last week, we sort of were studying these things called matrices, which are nothing more than collection of numbers. And like regular numbers, we did a lot of things to them. We added them, we subtracted them, we multiplied them. We found these things called determinants, so on and so forth. Well, over the weekend, I ran across two pretty interesting matrices. This matrix here, 2, 1, 1, 3, 2, 1, and 2, 1, 2. This matrix and this matrix here, 3, negative 1, negative 1, negative 4, 2, 1, negative 1, 0, 1. And they seem like very ordinary 3 by 3 matrices. So what's so special about them? Well, the place in which I got these matrices told me to multiply them. So I was like, okay, I have some spare time on the weekend. I want to have some fun, so I decided to multiply these guys. So this is a 3 by 3. This is a 3 by 3. So first of all, I want to make sure it wasn't a joke. It was possible to do this because the inside numbers match. And more importantly, the size of my answer is going to be a 3 by 3. Right. So I know I'm going to have 9 spaces to fill. Hey, can we not talk while I'm talking, please? Thank you. So I'm just going to go in order from the top left onwards. So from the top left, that's going to be row 1 with column 1. So if you do the inner product or the dot product, I'm just going to say this out verbally. I'm not going to write down my scratch work. So 6 times 3 is 6. 1 times negative 4 is negative 4. 1 times negative 1 is negative 1. 6 plus negative 4 plus negative 1 is a 1. So let's go ahead and do this part here. That's row 1, column 2. So I'm using row 1 with column 2. So I'm just going to say this out loud. 2 times negative 1 is negative 2. 1 times 2 is 2. 1 times 0 is 0. Negative 2 plus 0 is 0. On and on you guys go. So you guys know how I'm multiplying this guy, right? So I'm going to fast forward through it. So if I do the top right corner, I got a 0. If I do the left middle, I got a 0. If I do the straight up middle, I got a 1. Right middle, 0. Bottom left, 0. Bottom middle, 0. And right bottom, I got a 1. So this is a very interesting matrix here. It has a 0 everywhere, except 1 along the top left, bottom, right diagonal. Now, in the world of matrices, this guy here is called an identity matrix. Right. Specifically, it's a 3 by 3 identity matrix. Identity matrices is the matrix equivalent of the number 1, right? So what happened here was these two matrices, when I multiply them together, they sort of did stuff to each other to give you basically the equivalent of number 1. We see this happening a lot in regular math, right? The number 3, for example. What would I multiply the number 3 by to get to the number 1? Oh, that's just 1/3. It works with negatives as well. Say negative 5. What number would I have to multiply negative 5 by to get the number negative 1? Negative 1/5. Right? And it works with fractions. 2 7ths. I would have to multiply by 7/2 to get to 1. So in the world of regular arithmetic, naturally there are numbers in which when you multiply them together, they will do stuff to each other to give you out the identity, the number 1 in this case. In the world of regular arithmetic, these guys here, these pairs of numbers, they have a special relationship to each other. We call them multiplicative inverses. Hey, in the world of numbers, these guys are inverses of each other. So it sort of makes sense in the world of matrices, there should exist inverses as well. And it's sort of an important concept because let's summarize again. Last week we did adding matrices, we did subtracting matrices, we did multiplying matrices. Well, the idea is in the world of matrices, you can't divide. There is no division in matrices. So that sort of poses a problem for us. Well, if there's no division, how do we get rid of things? And the idea is inverse. Now, I was given these two matrices, right? But in life, they're not just going to hand you the inverse on a silver platter. We have to find it. How the heck do we find inverse matrices? That's the one topic. That's the only topic that we're going to talk about today. Ironically, I think it's easier to see this with a big example. So we're going to explain how to do this with a 3x3, and then we'll apply the steps to a 2x2. So finding inverse matrices. Now, like with all things in math, if you were to do independent research, if you were to Google, Khan Academy, whatever, there's a bajillion different ways to find inverse matrices. I'm only going to show one particular method. I think it's the simplest to understand, but if you disagree with me, feel free to, again, do independent research and do whatever method you want. But I'm going to show this method here. We're going to find inverse matrices using something called an adjugate matrix. What is an adjugate matrix? Well, again, it's easy to see with an example. So let's find an inverse matrix. Step one. If you want to find the inverse of a matrix, you want to find the determinant first. Right. So suppose I had matrix A, and his matrix was 1, 2, 4, negative 2, 2, 2, 2, negative 2, negative 3. Right. Step one is to find his determinant. So what is the determinant of matrix A? Well, it's a 3x3, so we got to do that column copying technique. 1, 2, 4, negative 2, 2, 2, 2, negative 2, negative 3. And I'm just going to copy the first two columns. 1, 2, negative 2, 2, 2, negative 2. Can I fast forward through this? We've done determinants enough that you guys understand what I'm doing with the diagonals. So I'm just going to fast forward through this. I'm not going to show my middle work because we spent last week doing nothing but determinants. So for the first diagonal, we have negative 6 plus the second diagonal, that's an 8, plus the third diagonal, that's a negative 16, minus this diagonal, so that is what, 16, plus this diagonal, which is a negative 4, plus this diagonal, which is a positive 12. So that gives us, what's that? So that's a 2, so that's a negative 14, minus, that's a 24, which is a negative 38?
Yes.
Okay. Hold on a second, guys, because I did this earlier, and that's not what I got in my notes. So what did I do wrong?
4, negative 2, negative 2. It's supposed to be a positive.
Ah, thank you. This diagonal here should be a positive 16. My bad. That was my mistake. So that would make this a 18. That would make this a negative 6. Yeah, which is what I got in my notes. Thank you. So then step 2. You're going to transpose the original matrix. Right. Now this is going to sound weird. What the heck is a transpose? So if I have my original matrix, 1, 2, 4, negative 2, 2, 2, 2, negative 2, negative 3. What a transpose matrix is you take all the rows and flip them into columns. You guys done back there? Should get up to date with your tweets or Facebook, whatever it is you guys were reading there. We're up to date. Current events are good. All right. Glad we got that important news out of the way. So you guys can see here that the original matrix has this row this row, and this row, what a transpose does is takes those rows and turns them to columns. So you have this column, and this column. So I'd write down 1, 2, 4, negative 2, 2, 2, 2, negative 2, negative 3. So that's what a transpose does. You just take the rows and flip them into columns. That's not too bad, I hope not. All right. This is where things is going to get pretty weird if you're not paying attention. It's not hard, but it's going to be weird if you're not paying attention. Step 3, you're going to find the matrix of minors. Okay. What is a minor of a matrix? A minor of a matrix is the determinant of what you get left over when you cancel out one row and one column. The description is wickedly complicated. It's a lot easier to see with an example. So what we're going to do is take this matrix here. 1, negative 2, 2, 2, 2, negative 2, 4, 2, negative 3. Our matrix of minors will be the same size, so it's going to be a 3 by 3. So here's our answer here. Or not answer, but this is what we want. So I got to fill in something in that position. What will go in there? Well, you see how this is the same position in our matrix here? If you were to delete this row, or that column, and that row, what's left over? 2, negative 2, 2, and negative 3. What you do is you find that determinant, 2, negative 2, 2, negative 3. And then this is a 2 by 2. That should be easy. That's the crisscross subtract. I hope I don't have to show my work. That's just negative 6 minus a negative 4, which is a negative 2. I did that fairly quickly, but that's a 2 by 2 matrix. I hope we're experts at 2 by 2 matrices. I put a negative 2 here. Rinse and repeat with the other position. So if I want to fill in this position here, I take this position, I delete the row, I delete the column, what's left over? 2, negative 2, 4, negative 3. I find the determinant. So that's going to be negative 6 minus a negative 8, which is a positive 2. I put a 2 there. You guys understand what's going on? So then if I want to find the top right corner, I take the top right corner, delete the row, delete the column, 2, 2, 4, 2, and I find the determinant. So that's 4 minus 8 is a negative 4. Put a negative 4 there. You rinse and repeat.
So depending on number, the position that you want to find, you're going to delete the
row in the column. And then find the determinant of what's left over. That's what we call a minor. You guys okay with that? Yeah. So is it okay if I fast forward through the rest? Yeah. All right. So if I want to find this this position here, I'm going to delete this column, that row. So we have 2, negative 2, 2, negative 3. So that's going to be negative 6 minus a negative 4, which is a negative 2. For the middle position here, delete the row, delete the column. We have 1, 2, 4, negative 3. So that's going to be a negative 3 minus an 8, which is a negative 11. For this position here, delete the row, delete the column. We have 1, negative 2, 4, and 2. So that's going to be a 2 minus a negative 8, which is a 10. Yes.
The center.
The
first one.
Yep.
You delete the top one instead of the second.
So for the center here, I deleted
the one next to it. The first.
Right here.
Yeah.
I deleted this and I deleted that. So.
Yeah. You did delete the first row instead of the second one.
For this guy here.
Yeah. You delete the first row.
Okay, so it's 2. Oh, yeah. Thank you. So what's left over is negative 2, 2, 2, negative 3. Thank you. So that's 6, 4. It's a positive 2. There you go. Thank you. What are we on? The bottom left corner. Deleted the first column, third row. That's negative 2, 2, 2, negative 2, which is going to be a 4 minus a 4, which is a 0. That's nice. Bottom middle. Delete, delete. We have 1, 2, 2, negative 2, which is a negative 2 minus a 4, which is a negative 6. And then last but not least, the bottom right corner. Delete, delete. You have 1, negative 2, 2, and 2. That's going to be a 6. Okay. A little bit of tedious math work because you have to do a lot of deletion, but it's just crisscross subtract, which I hope is easy. All right. So we're okay with step 3, matrix of minors.
Yeah.
Just, I mean, it's a lot of writing. I mean, 1, 2, 3, 4, 5, 6, 7. You got 9 spaces, but I think it's pretty simple. Step 4, create your cofactor matrix. So let's do some labeling here. This was, let's go back to step 3. This was our transpose matrix. Because this is our matrix of minors, I'm going to call it capital M. Okay? M for minor. We're going to create our cofactor matrix. Now, if you do the cofactor of the minors of the transpose, we call it an adjugate matrix. I'm not going to give you a vocab test for this class. If all those terminologies are too confusing, hey, what's a minor? What's a cofactor? If you can do it, that's all that I care about. So if you don't remember what cofactor or adjugate matrix is, just be able to do it. So the cofactor matrix is the adjugate of the M, which is your M matrix times this pattern here. Top left is always plus. Can you guys remember that? Top left is always plus. Then all you got to do is alternate. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, sure. So what was our minor matrix? I'm too lazy. I don't want to scroll up. From left to right.
Negative 4, 2, negative 11, 10, 0, negative 6, 6.
Okay. So what we're going to do is we're not going to do matrix multiplication. We're just going to do straight up corresponding multiplication. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So what does this mean? This means in the top left corner, multiply by a plus. Well, negative 2 times a positive stays as negative 2. In the top middle, you're going to multiply by minus. 2 times a negative is a negative 2. Does that make sense? So that's all you're going to do to find the adjugate. Just multiply the pieces by the positive, negative, positive pattern. So top right times top right is a negative 4. Middle left times middle left is a negative 2. So on and so forth. You guys understand what I'm doing?
Yeah.
So I'm going to fast forward through the results. So that's a negative 11, negative 10, 0, positive 6, positive 6. I promise you that's going to be the hardest work, step 1, step 4. To find the inverse, you just got one more step, and it's the easiest step in the world. But before we move on, are we okay with that? All right. Here's step 5. Divide by original determinant, which was step 1. So recall in step 1, our determinant was negative 6. So therefore, the inverse matrix is 1 over negative 6, dividing is the same thing as multiplying by the reciprocal, times the adjacent matrix that we found in step 4. Negative 2, negative 2, negative 4, negative 2, negative 11, negative 10, 0, 6, and 6. So if you distribute that guy in and simplify, you get 1/3, 1/3, 2/3, 1/3, 11/6, 5/3, 0, negative 1, negative 1. That is the inverse of that matrix. All these steps go into creating one matrix. Yes. So the question would be: here's matrix A. Find his inverse. The answer would be this guy here. That is the inverse of matrix A. I know it looks very crazy, complicated. Oh, 5 steps, that's a lot of work. And I'll admit, it's not a one-step process. But once you get the hang of it, it's actually a simple process. Just know these 5 steps. Question?
Why did the sign change?
Oh, because I'm distributing a negative number. So a negative times a negative is a positive. So on and so forth.
So what if no inverse exists?
No inverse. So what would it look like if no inverse exists? Do you agree that step 5 is to divide by the determinant? Well, what's one number in the whole universe in mathematics we can never divide by? 0. So if step 1, so very good question, nice segue. If in step 1, determinant of A equals 0, no inverse exists. So if you ever get determinant equals 0, you can stop. You're done. Boom. The answer is does not exist. You guys okay with that? Okay. It's not hard. It's just multiplying, adding, subtracting, but it's getting the right steps in order. And that's what I want you guys to practice today. Can we get all 5 steps down, crisp, clean, without making arithmetic mistakes? The hardest part of today's lesson is doing your adding, subtracting, not making a mistake. But you have your 5 steps in front of you. Hopefully you can will follow through. Now this example was for a 3x3. It's the same steps for a 2x2, but it should be like a lot faster. So let's just do a quick example of a 2x2 and see how these steps still apply. So let's find the inverse of, and I'm just going to pick one by random here. So let's say, -1, -2, 5, and 0. And I'm going to call them matrix A just to make my notations easier. You guys ready? Yeah. Step 1, find the determinant. Well, since it's just a 2x2, it's just crisscross subtract. That's easy. So that's going to be 0 minus -10, which is a positive 10. Step 2, find my transpose matrix. My transpose is take all the rows and flip them into columns. So that's going to be -1, -2 going down, 5 and 0 going down. Are we okay with that? Make your minor. That's just deleting a row and a column. But this should be super duper easy for a 2x2 because for the top left corner, if I delete the row and delete the column, there's only one number left.
How do you know A is equal to 2?
Because to find the determinant, you do crisscross subtract. So what's -1 times 0? 0. Minus, what's -2 times 5? -10. 0 minus a -10 is a positive 10. All right. So when I do my minor for a 2x2, it's just the single number itself. So the top left corner is 0. Top right corner, -2. Bottom left corner is 5. Bottom right corner is -1. Guys okay with that? Now it's time for the adjacent. So the adjacent of M is just taking that M matrix and multiplying by the alternating pattern. So top left corner, I would start with the plus. So it'd be plus, minus, minus, plus. You okay with that checkerboard pattern? So then we go ahead and what do we get? 0, positive 2, negative 5, negative 1. And then the last step, a inverse, is to divide by the matrix, by the determinant. So our determinant was 10, so it's 1 over 10 times that matrix. So that gives us a 0, 1/5, negative a half, negative 1/10. So the question was our answer always going to be in fractions? Normally, if you're just making up random matrices, inverses are going to be ugly looking. They're going to be fractions. The very first example that we did here, I picked this specifically because the inverse were nice whole numbers, but usually they're going to be ugly and messy. Yeah. But that's the inverse matrix. Not too bad. I hope not. Again, once you get a feel for these 5 steps, it becomes pretty simple. Okie dokie? All right. So that's all you're practicing for today. We are not going to be using them until tomorrow, but we got to have this skill down cold. If I give you a 2x2, if I give you a 3x3, can you find the inverse? And it's just those 5 steps. They seem funky, but, we got to be experts at it.